So it's time I switched on my controller. It's 2019, and there's been kind of a theme in the past couple of years, which has been quite interesting, kind of globally. I don't know if you've noticed, but that theme is liars and lies. Yeah, there was no way I couldn't put this up. So it seems that kind of everyone's at it. Politicians lie all the time. Well, that's nothing new. But the amount and the frequency of these lies has seemed to got an awful lot worse, and it seems to have kind of spread everywhere. And it's kind of got to the point as well where people are so used to lies that it's kind of just become the new normal. It's actually kind of quite difficult to tell what's true now, not because we don't do our own research, just because there's just so many lies, and it's difficult to kind of trust different things. And this is kind of a global problem, and it's everywhere, except us, right? Yeah, we're engineers, we're scientists, we're programmers, and we don't lie. Our stock in trade is truth. It's what we do. You can't make 2 + 2 = 5 unless you're very, very careful with advanced mathematics, and generally speaking, you can't at all in programming. You can't kind of, convince a machine to do something which it isn't designed to do at a kind of a fundamental level. You can make up whatever lies you want about theory, and you can tell them to people, but it doesn't actually mean it's true or demonstrable. Yeah, well, I mean, we always tell the truth because that's kind of what we're all about. The thing is that we actually do lie quite frequently to ourselves. And that's something which is kind of in the way of a few things. And this is comes back to the previous talk. We tell ourselves lots of interesting lies. We tell ourselves that we have, say, for instance, infinite memory. I don't know when was the last time you thought about allocating memory if you're writing applications. I mean, if you're not a kernel engineer, then fair enough. But we've got things like automatic allocation, deallocation. We've got memory paging, I've had done for a very long time. We've got garbage collection, which means we don't have to worry about sort of, freeing up memory and that sort of thing. And the overall lie is that we don't need to worry about memory anymore at all. It's just kind of there, and it works, and it does its thing. And then there's the lie about infinite storage. We have terabytes of disk space now. It's even really fast because it's SSD. And we've got exabytes of cloud disk storage. We have so much storage out there, as long as we're connected, that realistically speaking, we will never be able to fill it. It's infinite. We don't think about it. When was the last time you kind of like wrote something to cloud storage and seriously expected the error callback to actually hit? It's probably not going to happen. This goes on. There's infinite performance. We have multi-core threading, we have gigahertz, and very short to be terahertz in terms of like actual clock cycles. We have more and more efficient chips. We have many of them. We have many more chips in single machines, many cores. Concurrency and serverless computing, the idea, again, of cloud engineering where you take something like, I don't know, AWS, and you pretty much just throw tin at the problem until your performance issues go away. And it's so cheap that you can actually just do that. You don't really need to worry about that. So there's no reason to kind of think about this in the first place. You can assume that you have infinite performance because the resources required to give you that are so negligible. We pretend that we have infinite bandwidth. We have gigabit fiber connections. To give you an example, my recent company, Passphere, we just got our first office in Wellington, which is awesome. And fiber, of course, being who they are, they haven't actually managed to get us a fiber connection yet. So they lent us a 4G modem and Wi-Fi, and that's what we're using. And it's perfectly adequate for our needs. Now, fair enough, we don't use a lot of data, but it's absolutely fine. And I can sit and, like put my Psytrance on YouTube and kind of get about my day, and it's all great, no problem at all. 5G and beyond will give us even more bandwidth. The thing is that we realistically speaking, we really don't think these days about actually that sort of transfer, because most stuff, especially API, app sort of stuff, the amount of data is so small compared to the bandwidth that we just don't care. We don't think about it. All of these are lies, and they're lies that we tell ourselves. Now, you're probably thinking what the, because they're not really lies. These are more like abstracts or things which are negligible, things which aren't really, we just don't have to think about. They're not lies, right? Well, I disagree. Let's go back to a much simpler time. And this is kind of like a personal story of how I did this sort of stuff. It's 1986. I am younger than I am now, and let's just leave it at that. This is a Sinclair Spectrum Plus 2. My parents had bought me one of these things. Let's just take a tangent for a second and work through its specs. Right, now, this is just compared to sort of modern machines. This thing runs at 3.5 megahertz in a ZAD processor. Most of those instructions are multi-clock cycle. You have 128 kilobytes of RAM if you put it in the right mode. You have 48 kilobytes of tape storage, which takes 20 minutes to load from an actual audio cassette and may or may not work, which is really irritating. And you've got these, absolutely awesome graphics, which are fantastic. Now, here's the thing I didn't know. What I didn't know was that my parents were actually kind of barely getting by. They were really good at hiding all that stuff from myself and my brother. And they'd kind of scrimped and saved to buy this computer for us. And that was great, but they couldn't really afford to buy games. So there's really only so many times you can actually get through Manic Miner and Paddington's Garden Game before things start to get a little dull. And because I was an extremely antisocial child overall, I decided to kind of take a look to see if it could do more. And of course, in the Spectrum, you have this concept of BASIC. Now, BASIC was awesome from my point of view because you could type things in and make it do stuff. And I mean, it didn't look a lot like games, but you were causing the machine to actually do something. And that was fascinating. And I was like, right, well, I mean, surely people must do kind of more of this. And I was right. All the magazines, like Your Sinclair, that sort of thing. And this was a time whenever they didn't just review games. They had, full sort of like 3- and 4-page sections of stuff to type in, these huge lists of instructions you could type in BASIC to make stuff happen. And like I said, because I was, really very poor in the social skills, I spent a lot of time with this stuff typing everything in, and it was awesome fun. It was great. It even got to the point where I started to kind of modify these things you have to type in yourself. I kind of started thinking about it. I was like, right, well, there's structure in here. That must make sense. And some of the magazines were really good for that. I was like, well, this bit does this, and this bit thinks about this. This is a thing called a variable, I mean, this is an operation. You've got bits of code, I learned it was called, which don't happen unless you're doing certain things at certain times. And I went, oh, okay, that's absolutely fascinating. And this went on to the point where I was actually able to write very basic games kind of on my own, which incidentally didn't make me any more popular than I had been before, but that's not the point. So fast forward to 1992, and this is where, as it happened, my parents had come into a bit of money, so they gave me an upgrade. They bought me an Amiga, and this thing was amazing. I mean, when you come after the sort of graphics, which we'd seen on the Spectrum and that sort of stuff, but just as a tangent, let's just, again, take a look at the sort of specs of this machine compared to modern machines. You've got a 7.14 megahertz MC68K processor. You've got 512 kilobytes of RAM. I mean, that's 4 times more than the Spectrum. And for 400 UK pounds, you could buy a little extension that went on the bottom that gave you another 512 kilobytes and got you all the way up to a megabyte. It was amazing. We've got these 3.5-inch floppy disks, which are dirt cheap because you can buy them HD and buy them in bulk and everything else. And they're 880 kilobytes, and they don't even take that long to load. So the Amiga was, I mean, I'm not going to go on about it. I don't suffer from Amiga persecution complex anymore. I go to meetings, it's fine, it's good. So the Amiga, I will rant about it for a second because it did have some amazing things, like the custom graphics and sound chipset. Compared to the Spectrum, this was just incredible. This was amazing. And the nice thing, of course, was that there were still these magazines with cover discs and stuff like that. And I could actually buy a few games now, which was nice. And I really got into it. More kind of as a gamer, as just a kid playing games and everything else. But the problem is that the bug had bitten. And I missed being able to get the machine to do things which I wanted it to do. And fatefully, I have no idea exactly when it was, but there was a particular cover disk, I think it might have been Amiga User, which had a basic copy of Amos Basic on it. So I started playing about with this. And it was kind of like the Spectrum, except with better graphics, and you could actually make things move, and you weren't limited to two colors per 8x8 pixel, and it didn't take 20 minutes to load off tape. And playing about with this, Amos Basic. Now, of course, I had no manual for this thing, so I had to figure it out broadly myself. I remember spending what seems like months, but must have been days or weeks, figuring out how to do something at Amos. It's kind of a long way. And then someone would say to me, oh yeah, but you just do this, and it's a one-liner. And I'm like, all right. And this was my first exposure to programmer stress, which was awesome. And of course, the Amiga had much better graphics. I have a bit of a sort of an artistic bent, although I don't like telling too many people about it in case they actually ask me to design something and I embarrass myself. But on another cover disk, we had stuff like Deluxe Paint. So I was actually able to bring in, you know, some graphics, actually able to write stuff in and everything else. And that was fantastic. And again, I got to the point through typing in stuff and through just actually creating my own and sort of thinking about it, these little games, and I gave them to my friends. And this still didn't make me any popular, so I'm not winning here. But anyway, we're going with it. Okay, the thing is the games as well, because we could actually buy them. And like all kids, I mean, you kind of want to cheat a little bit at your games or do better than other people and that sort of stuff. And we got one of these, the Action Replay Mark III to tell. And this thing plugs in the side of the Amiga. And that freeze button, you can hit that and it kind of freezes the whole machine and takes you into this, this sort of editor, this sort of like UI sort of thing. And then you could type in like cheat codes and that sort of stuff from magazines or whatever else. And the thing is, it had a couple of different modes. It had really basic sort of modes, just, you know, you type in literally this digit code that you got in the magazine and you got infinite lives. But for the more advanced users, it actually told you, right, well, if you go and modify these bytes here, these instructions here, then you can do some really interesting things with these games. The Action Replay Mark III had a built-in assembler-disassembler. And that opened a world for me, suddenly. I was like, oh, right, okay. See, this looks a bit like Amos. I mean, it's even the same color as screen. I was wrong, obviously. But, you know, if only we wrote everything in Amos. But suddenly, it occurred to me that there must be, this was a language, but there must be something in here which makes sense. This is how you actually drive the machine to do things overall. And that's when everything started to open up properly. I started to learn a bit more about what was going on, and suddenly the instructions started to sort of make sense. The thing is that I discovered I needed to know an awful lot more than just what these little acronyms meant. I discovered that I needed to know about how the electronics of the machine worked. Because what's this thing called memory? You know, what is a register anyway? I mean, how does that work? What are these stacks I keep kind of hearing about? Why can't I branch, you know, over 4 kilobytes of memory? I need to use a jump instead. That doesn't make any sense. It's weird. Surely there should be just one instruction. So now, I don't think there's really anybody here who's not going to get this. The next slides really won't make a lot of sense. I expected to have to do a bit of actual education as part of the educational mini-conf. Okay, this is a library. Now, a library was a place where you could go out and you could borrow books. Now, books are a little bit like printouts. You know, if you print out loads of stuff and stick the edge together, you get this thing you can carry around and you can read them off the books and everything else. I think we're all kind of old enough to get that, which is maybe both a compliment and an insult. But anyway, previous to the internet, these were, of course, occasionally useful. This is my local library in my hometown. And I was able to go there because I'd always been a little bit into electronics. I'd always like kind of wired up little motors and switches and stuff like that. And learn, of course, the first thing I had to do was actually understand what all these little acronyms meant that I saw coming out of the Action Replay. And what I managed to pick up was the Amiga Hardware Reference Manual, which had tons of what I later learned were C examples. But by then, I could already see that there was structure in the code I was looking at. And I could see kind of how, even though the language in there wasn't what I was used to seeing, it kind of made sense. I saw the patterns between them, and that started to make sense as well. And then, of course, not actually this book I didn't get, but the 68K kind of reference overall to take a look at what the actual chip was doing. That, of course, wasn't enough. I had to learn as well about how the electronics of the system work, what an address bus is, what a data bus is, what clock signals are, how these all things come together, how you get memory addressing, which of course led into 74 series logic and all of this sort of stuff. I mean, it's ancient stuff now, but it was absolutely fascinating to me because I kind of learned, you know, sort of, it's a bit of a boast, but from first principles, how the machine worked from the ground up. And that got absolutely fascinating because for some reason it just made sense to me. And I ended up doing some really amazing things with the Amiga. First with Amos Basic, and then with actually writing directly in assembler, literally just using the action replay, and then moving on to, there was a C compiler on another cover disk. It's really all about cover disks, this is great. Or Turbo Pascal or something, you know? And I wrote some really amazing things, none of which you can see because I'm not a famous Amiga programmer at all, and that's just kind of it. Overall, this entire thing, what has this got to do with lies? This is kind of my story as an engineer. It's where I kind of started the whole thing. So why did I just say that we're all liars? Maybe it's a better way to put it as a metaphor. Like Terry Pratchett and Wintersmith said that a metaphor is a kind of lie to help people understand what's true. And maybe the lies I've been talking about, like infinite memory and infinite performance, infinite storage, and infinite bandwidth, are kind of more like abstracts and metaphors around away from the truth, but they help people understand what it is that we have. And what it is that we have are advanced programming concepts. What we have are languages and language features and systems and frameworks that allow us to pretend for ourselves that these lies are true. And that sounds an awful lot like magic, doesn't it? Modern languages are magical. Okay, some modern languages are slightly less magical than others, but that's not the point. They are magical, right? They do things which, unless you have a very deep understanding, look like magic. We have this whole concept of like language generations, and I'm going to take them kind of from the most magical to the least magical. Let's go for language generations. We've got the fictional 5GL, right? Fictional 5GL, JDWIM. You may have heard of this. It stands for Just Do What I Mean. And every JDWIM program has one source file with one instruction that says just do what I mean. Sometimes it's shorter, you know, because that's better for bytes. And what that means is you're instructing the computer to just do what you mean. You're not even telling the computer what it is that you want to do. You're saying, I want to do a thing, and it's your job to figure out what that thing is and how to do it, and present the results to me or do what I mean. So just do what I mean. That is most magic. That is Battle of Hogwarts level of magic. That is huge amounts of magic. And it sounds ridiculous. And until recently, JDWIM was kind of a joke. But the truth is, we live in a world of advanced heuristics. We're taking a look at, you know, machine learning. We're taking a look at this AI thing, which people keep misquoting and misunderstanding. And we're actually not that far off. We've got facial recognition software now, which can read emotional intent. We've got, you know, semantic analysis and entity analysis on text, which can kind of maybe not figure out, but quantify, you know, emotional response and sentiment response from things. So we can even bring this sort of stuff in. We can use this sort of thing. We may be approaching a time whenever 5GLs are actually possible. But we've been saying that for 40 years. So anyway, let's move on. That represents most magic. You have 4GLs, right? I think SQL really is the common one. I bring Python and Ruby in there because the kind of definition of a 4GL is where you teach, you say to the machine, I want to do a certain thing, but you don't tell it how. It's up to it to figure out how that works. You give it a instruction, usually in something like a real human language, and you say, I want this to happen, and it goes, all right, and it gets it done. And you don't know or care how that happens. And that's still pretty magical. We move on then to 3GLs, and this is where most people kind of like, you know, stop or start, depending on which way you want to see it. Java, Basic, Pascal, C#, C and C++. Now, I'll get to those in a second because there is a definition of abstract here. The thing about these 3GLs is that you're still talking in abstracts. You may be telling the machine not only what you want to happen and also how to do it, which is the difference between that and the 4GL, but you're still talking in abstract. You're still saying, right, well, I've got this thing which is object orientation, and I want to see everything in terms of classes, or I want to use prototypical inheritance, or I want to be able to use mix-in functions in Ruby, or all that sort of thing. That's where all that sort of stuff comes from. A 3GL is the level of magic most people kind of learn at university, unless they go any further. It's definitely the sort of level of magic where people start from if they don't come from, shall we say, a traditional background in terms of how to code. You go to the 26-week course on how to do something because you've been a web developer and you actually want to learn how to code properly. Generally speaking, they're going to drop you in a 3GL. You're not going to see anything below that. For reference, of course, 2GLs, second-generation languages, are pretty much just representation forms of the actual bytes that chips are actually running. And 1GLs, first-generation languages, are the actual bytes running on the actual memory which the machines are processing. So that's kind of where we're at. My point here is that there are a whole swathe of programmers out there and engineers out there who still don't understand that 3GLs are still pretty magical. And they're especially magical if you haven't done anything below them. And it leads to, of course, what we kind of know as cargo cult programming. Now, I've always been slightly confused by the term cargo cult programming. I mean, it obviously comes from the cargo cults in the Pacific after the Second World War, but it seems to me that, they built all of this stuff out of bamboo, but the planes never actually came back. They put an awful lot of time and effort into something, built this whole thing based upon pure faith, and because they're abstract, because their model wasn't accurate, these things never happened. Now, I'm not going to talk about large government projects, which we've all been on, but the term doesn't really make sense to me. I prefer a different term, which I call rain dance programming. Now, rain dance programming works like this. You learn to do a rain dance, and it rains, and that's great. And you learn to do the rain dance really well, so it always rains when you do it, and it's fine. And then eventually you even start modifying bits of the rain dance so you get different types of rain. Ask anyone from Seattle, that's how it works. And that's fantastic, because you do these rain dances and it always rains until one day it doesn't. And you have no idea why. Because you learned to do a rain dance. You had no fundamental understanding of what you were doing. And as such, someday, something beyond your control went wrong. You ended up in a different way of seeing the world, different abstract. Maybe something under you fell apart. And it didn't work. This reminds me of a story from the jargon file way back. I don't know if anyone remembers the jargon file. But it's Tom Knight and the Lisp machine. And the story goes that a novice was trying to fix a broken Lisp machine by turning the power on and off, by cycling the power. Knight, seeing what the student was doing, spoke sternly, "You cannot fix a machine by just power cycling it with no understanding of what is going wrong." The story, of course, then goes that Knight turned the machine off and on and off, and the machine worked. And that was because he knew what he was doing. This is what I'm asking people to really do here, which is to kind of look beyond your abstracts. We've learned, and we largely teach these things at a certain level, and they're magical. You can do a lot better than just like assembler for this sort of stuff. But to be honest, 68K assembler, if I just have to pick one out of the air, is actually pretty good for this sort of stuff. Because you have some things which are kind of like really obvious, even if you've done a lot of standard programming, as it were. But it is very constrained as well. So you've got 8 general purpose 32-bit data registers, address registers on the Amiga. You had 24 bits of continuous non-page address space. So that's about 16 megs worth. You've got arithmetic bit and logic functions, but you've got no floating point. You're using libraries for all that sort of thing. You've got conditional branch addressing and jump addressing, but with tests, but you don't actually have anything that resembles a control structure based into the assembly itself. I know some forms of assembly do, but this is old enough to not have that sort of stuff. If you want to do things like while loops, for loops, that sort of stuff, you kind of got to build them yourself. But you do have some things which are a little bit magical, like pre and post incrementing and decrementing registers. You can kind of stream the results of a calculation out to memory using a stack, or you've got proper stacks, and you've got this beautiful magical instruction. It's only 6 bytes long, which allows you to save most or all of your entire register stack to memory and then bring it back again, which is really good for writing kind of, routines which you don't want to influence the rest of the machine state for. So you've got a little bit of magic in there, and you can kind of see it in sort of a structured way. But generally speaking, I'm suggesting we should actually start teaching this sort of stuff, because I think we live in a world with too much magic in that sort of way, and that's one of the reasons, I believe, why modern software can be problematic, why it can be slow, why it can be inaccurate, why it can be faulty. I want to live in a world kind of with no magic, or at least magic which we actually understand. No, don't worry, I'm not actually saying that we should actually get people to code in assembler to actually build things in assembler, because that would be like trying to dig a road tunnel with a teaspoon. It's not a good idea. It's going to take forever, and it's too complex. We need a bit of magic from point to point. But I do suggest that we do need to teach this and learn it as an exercise, because learning assembler changes how you think. And just to step out of it, although I really want to kind of go with this as an exercise, some IoT devices are actually still this basic. You go down to the microcontroller sort of level, you may actually have to think about this sort of stuff. You may have to think about the constraints of the memory, the constraints of the power of the device, literally power of the device, not just in terms of performance, but also in terms of the actual electricity moving through it. This changes how you think if you're able to do this sort of stuff, because constraints are good. If you are able to code at this sort of level, you're not thinking magically. You're not just doing a rain dance. You are building up fundamentals overall. You need to go and study extra things here and there. You need to get out of your comfort zone. You need to go and understand the domain model. You need to maybe go and complete that MAS paper, which you failed in uni, because you need to understand what is going on and build it from scratch yourself, even if there are libraries to do it. Learning assembler will change your thinking so that even if you're able to use something else someone has done, do not repeat yourself if there's great libraries out there doing them, and do not write your own crypto, just by the way. We all know that. But there's nothing wrong with implementing your own crypto which you never ever use, so you understand how it works. Constraints like this are good. Also, minimalism is good. If you're used to working on machines which are running single core at 7 megahertz and they've got half a mega RAM and that sort of stuff, you're thinking small, everything's efficient, not because it's a good idea, but because you have no bloody choice. If you don't make it that small and that effective, it will not work, or it will not work in a performant way. Also, you're going to have to structure stuff an awful lot better. You're going to have to think about the real structures of what is going on when you're coding from scratch, or you're going to have to understand the structures well when you're actually looking at other people. And that means less code. And less code, very simply, it means less bugs. There is a direct correlation. The less code you have, the less there is to go wrong. If you've really thought about it, if you really deeply understand it, then there's going to be less wrong with it in the first place. But even just on the metrics, less code is less bugs. We all know this. Simplicity is also maintainability. I don't know whether you've seen real assembler. Any kernel engineers in the room have probably done something like that. But real production assembly is filled full of comments. There's a comment on nearly every line. You describe every single thing you're doing. I'm not suggesting we do that for higher level languages, but the truth is putting comments and telling people what you're doing, or telling yourself what you're doing 6 months in the future, is a good idea. How many times have you done a git blame and thought, oh yeah, well, some bloody idiot has completely messed this up. This is a mess. So who would have done something like this? And you do a git blame and you find, oh, it was me. Right, okay, and that's only 6 months on. Describe your code. Simplicity is also maintainability. It's proportional maintainability. And that simplicity overall is described. If you keep it simple, you don't have to describe it so much. Then the final point, and in many ways the most important one, especially in a world where you can just throw it in at a problem until it goes away. Performance is a function of deep understanding. I argue that is true regardless. There are very few systems, if any, out there, I believe, tell me if I'm wrong, which are performant, which do not come from a deep understanding of what it is that you're actually doing, what it is that you're trying to do. If you get that right, a lot of this performance just kind of falls out of the bag. And I think we should teach this from scratch, and I think we should do it with assembly, Not by simply saying, oh yeah, and say for instance JavaScript, we could have a large number of elements here, we put them in an array or we put them in a map. They do have a unique ID, so why not put them in a map because that's more performant to use. That's theoretical. If you've had to write those control structures, those ADTs yourself in assembler, you're going to have a strong appreciation of why it is and why it does that. That's kind of a thing. Overall, I'm saying that these are a bit like katas. These are a bit like forms in a martial art. These are things which we can do, which are not necessarily useful in and of themselves, but they kind of change your thinking. They develop a certain sort of, to use a metaphor, there's another lie for you, muscle memory, you know? A kind of a way of thinking about the world and a way of thinking about the systems you're writing, which are fundamentally better. And you don't think about them, that's the point. You do it a certain way because it's kind of obvious. There's a saying in Wing Tsun Kung Fu, if you can't do it slow, you can't do it fast. And I suggest that we say to our students, to our mentees, to the people who we're trying to teach to do this sort of stuff, and occasionally to ourselves, that we should slow down and we should actually do it from fundamentals in something like assembly or something at that low level. Thank you very much for listening.
We have plenty of time for questions.
Yeah, we do. Please.
You mentioned the phrase of the abstraction. We don't need to concern ourselves with the latest thing.
Absolutely, absolutely. Leaky abstraction is kind of what the concept was about. If we think too much in terms of abstracts, we lose the fundamental understandings. Abstracts are great because they allow us to make ourselves more efficient and do what we want. Definitely build things faster, as anyone, I mean, NPM downloads internet for you, you know. But if we rely on them, if we start to believe that the map is the territory, then we end up in a situation very rapidly where you get confused by your own abstracts and you lose the performance and gains of that and everything else, and the whole thing becomes kind of pointless.
Yeah, I was just curious if the title of the talk was in any way related to Bob Martin of the Agile Manifesto and Clean Code, who read an article a while back called "Make the Magic Go Away."
Yes.
Yep.
That's kind of, it's not one I read before I kind of planned this, but it's just, I suppose it's the difference in a sort of a culture. In my own BlackRaven Dojo, I try to teach the culture and the history of programming and engineering as much as I teach actually how to do it. And in many ways, this is kind of the issue. Like I said, sort of during the presentation, the problem is that we kind of teach from the middle out, whereas I think that we should teach from the ground up. And there's nothing wrong with magic. I'm not saying magic is a bad thing. I'm saying that if you're going to use it, you should understand how it works. Absolutely, absolutely. I think it's one of the most, apart from the fact that, let's face it, we're all kind of, we're all geeks and nerds and that sort of stuff is fun for us. I would argue if it's not fun for you, maybe we're in the wrong career, but that's a different thing. It is take, an hour of the evening or whatever else and just kind of work away. Take a weekend or something and go and learn a new language just for the hell of it, to find out how it works. I did that with Rust and thoroughly scared myself in terms of how rusty I'd got. That's not actually supposed to be a joke. But yeah, the thing is that every language you learn will actually make you a better programmer in every other language you know, because it changes the abstract of it. It's not something I went into here, but it's the same as people learning human languages. Kids who grew up bilingual are better at learning new languages than kids who grew up monolingual. And the reason for that, I'm told, now I'm not a psychologist, so again, correct me if I'm wrong, is that bilingual kids abstract concepts into something which does not have a sound in their head. They have to, because there is more than one sound associated with a particular concept. And that means that it's quite easy for them to tag on another set of sounds to the same concepts because they're already abstracted. Whereas monolingual kids grew up with a hard link between the abstractions they have, the concepts they have, and the sounds those concepts are expressed in. I argue it's the same in software engineering because we are literally talking about languages. Every language you learn corrects your abstracts out. It moves your concepts away from specific implementation and specific implementation patterns. It allows you to think about things in different ways, especially when you break out of object orientation, when you take a look at something else completely, when you learn Lisp because you hate yourself and it's not Haskell yet. This was great, don't get me wrong. But that sort of thing, learning to do things, especially when you look at it and you go, oh, who would do it like that? That's the trigger point. That's when you should learn it, because that's something which you find challenging. That's something which is changing your abstracts, changing how you think. I think for a lot of modern engineers, taking a look at assembly in that sort of way would be helpful. One more question.
Hi, it's BDL. Really appreciate the talk. I have argued this general concept a number of times. I would quibble with one little detail, though, and that is in your layering structure, I personally think there's very little distinction between machine language and assembler. It is interesting that my own history, I learned the hex opcodes for the 1802, and it was years before I understood that that wasn't assembly language. It wasn't until somebody showed me an assembler, and I was like, oh, this is interesting. It automatically manages branch address distances. I think the distinction between those is really insignificant, though, compared with, for example, the distinction between C and C++ or anything else that was in your third generation line. And I've actually personally discovered that using sort of KNR style C is almost as good for getting the sort of attention on the level of detail that is actually useful for driving performance and sort of underlying systems understanding as trying to push people all the way to assembly language. I'm actually a huge fan of assembly language. Perlis once said that any new programming language that didn't change the way you thought about the problem wasn't worth learning.
Yes.
That led me to assert later that if it couldn't be written in Forth or Scheme, it wasn't worth writing, or didn't need to be written. But in my own experience dealing with kids, it's been really interesting that thinking of C as portable assembler and thinking of it less as a high-level language is an interesting thing to do. It's of course true that when you start dealing with lists and all sorts of things, you can sort of add more layers of abstraction in. But when I sort of unwrap what you're talking about, to me it's a lot about how do you break through the layers of abstraction and get back to what the machine is actually doing and how resources are actually being allocated and used.
And I agree with you. C, to be honest, is probably a better idea. If we teach like real fundamental C in that sort of way, then that kind of, it breaks the point where we're coding on AMD64, we're coding on ARM, all that sort of stuff.
Yeah.
I'm also of a vintage, although not professionally, where quite literally, the bit I kind of missed out because it would have been super boring is just before I discovered what an assembler was, I was actually looking up the bytecodes for 68K instructions and literally poking them into memory and running them. Yeah, that lasted about 3 hours. Being able to do that, that's the difference between kind of, machine and assembler. And to be honest, I didn't come up with a generation system, and I've always wondered why, because 1 and 2 really seemed very, it's driven by ideology, I think, the difference between the two. You have the difference between any translation to the machine. If you're typing it in hex, you might as well type it in binary. It's just going to take less time. I would argue then that assembler is just a semantic representation of those bytes, and maybe that's the reason for the theoretical difference. But definitely in something like low-level C, that's the sort of stuff which maybe we can take them all the way down to and kind of expose them to assembler as, by the way, this is what it turns into. And it does it differently on different platforms. And that's good as well, because then we bring in the idea of abstraction across multiple different platforms. And that's excellent.